NumPy, Python's numerical computing package, has on its menu of discrete distributions 9 items, 9 discrete distributions that we can easily sample from with one simple line of code. It has a separate menu of continuous distributions listing 25 items, 25 continuous distributions that, once more, we can very easily sample from with one simple line of code. If you watched my video from a couple years ago titled The Menu of Probability Distributions, you might even have a sense for what happens behind the scenes when we sample from any of these distributions. But the point is that the menu of distributions is right there in front of us. It's sitting ready for us to start sampling. But if you're just getting started with probability, you might be asking yourself, why would you care to go and sample from any particular distribution? We'll answer that question with a Monte Carlo simulation of a real-life problem. But before we get there, and this is what I will spend most of the time of this video on, I will tackle the question that I remember having myself when I was first studying probability and statistics. It's the question of how is it that we, as the human race, landed on this particular menu of distributions? In other words, assume there's life on some planet around a different star somewhere. The question is, are the life forms performing science on that planet over there, looking at a similar menu of distributions as the one we're looking at? Or does their menu of distributions look completely different? Is the fact that we landed on these particular distributions a manifestation of the universe we live in, or merely of the lens through which we perceive and study the universe around us? The Poisson distribution tends to pop up a lot, and that is because a lot of real-world phenomena follow the Poisson process. On the other hand, the T, F, and chi-square distributions also pop up a lot, and almost exclusively because these represent the lens through which we look at the universe. Because as soon as we have a sample and we start asking questions about it, these distributions pop up. But they are an artifact of our sampling initiative and not a reflection of the world. Today we'll look at the Bernoulli process, the Poisson process, and the central limit theorem. And I'll make the point that these three phenomena explain most of the probability distributions that we have on our menu. So that's the plan for this video. Let's get going. We will use the term Bernoulli process to refer to a sequence of independent and identically distributed Bernoulli random variables. In other words, IID Bernoulli random variables. What's a Bernoulli random variable? It's a random variable that takes on only two values, 1 with probability p and 0 with probability 1 minus p. In a Bernoulli process, these variables are independent, and the success probability, or the probability of getting 1 as opposed to 0, is the same for every single trial. That's the entire definition of a Bernoulli process. In the particular Bernoulli process in front of us, the probability of success, or probability of a 1, was set to 0.3 in each of these Bernoulli trials. If we pick a random starting point in this sequence of random variables, in this case I picked the 15th one, and then look at the next 10 trials, you can think of this subset of the Bernoulli process as an experiment in which we're flipping the same coin 10 times. And let's say that tails represent the success event, so then in these 10 flips of the coin, we observed 3 successes. So let's make a note of that, and then let's take a look at the next random set of 10 consecutive trials, and once more count the number of successes. In this case, when we look at trials 32 through 41, we see that we had 2 successes in these 10 trials, and we'll make a note of that. And then, if we repeat this process again and again, every time counting the number of successes in 10 IID Bernoulli trials, let's see what it is that we observe. And let's repeat this experiment 100,000 times so that we get a good sense of our empirical distribution. Notice how closely the relative frequency of each bin aligns with the probabilities that come out of the binomial distribution with parameters n equal to 10 and p equal to 0.3. Evaluating the binomial probability for x equal to 4 gives us that value of 0.2001 that we observe in blue above the bin corresponding to the value of 4 of this random variable. If we kept repeating this experiment and go beyond 100,000 repetitions to millions, the relative frequencies in yellow would approach the theoretical probabilities in blue closer and closer, eventually converging to them. So the binomial distribution arises naturally from a Bernoulli process when we count the number of successes in a fixed number of trials. The probability of getting lowercase x successes out of n trials, each with probability p of success, is given by the binomial distribution with parameters n, p. Now let's go back to our Bernoulli process and this time ask a different question. We'll pick a random starting point, a random trial, and then from that point on count the number of trials it would take for us to get the first success. With trial number 15 picked as our random starting point, you see that trial number 3 was the one that delivered the success, therefore it took 3 trials for us to see the first success. So we'll record this number 3 as the realized value of our random variable of interest, which in this case is the number of trials it takes to get the first success. Let's repeat this experiment once more, and we see that this time around the success arrives on trial number 5, so we'll record number 5 as the realized value of our random variable of interest. And then we'll just repeat this experiment again and again until the empirical distribution materializes. Notice one interesting thing. It is theoretically possible that the first success never arrives. Therefore, our random variable, which tracks the number of trials until the first success, will take on the values 1, 2, 3, 4, and so on, the integers all the way up to positive infinity. And if we bring in the theoretical probabilities, we notice once more the close alignment between the relative frequencies and the theoretical probabilities dictated in this case by the geometric distribution with one parameter, lowercase p, equal to 0.3 in our case. So whether you are passively observing a Bernoulli process or you are actively building one because you are the one performing these Bernoulli trials, if you are interested in the number of trials until the first success, and you're interested in computing the probability that the first success will arrive on the first trial or on the second trial, or on any one particular trial or collection of trials, you can compute those probabilities using the geometric distribution, which takes in one parameter lowercase p, which, notice, is inherited from the Bernoulli process. Now let's go back to our Bernoulli process and suppose that this time around we're interested in the trial on which we will observe the third success. And this can be generalized to the trial on which we will observe the rth success. Like before, we choose a random starting point and then we start counting trials until we register the third success. And the trial on which the third success is registered, that's the number we're interested in. That's the realized value of the random variable of interest here. We just saw that we got 7 as the first realized value, and now we see that we got 12 as the second realized value. And now we'll just repeat this experiment again and again until the empirical distribution materializes. And let me point out something about the range of this random variable. 3 is the lowest possible value for it because it takes at least 3 trials to record 3 successes. And it will take integer values going into positive infinity because the third success may never arrive. If we were to repeat this experiment even more times, going beyond 100,000 repetitions into the millions, then our relative frequencies in yellow would converge to the theoretical values listed in blue, and those theoretical probabilities you see in blue come from the negative binomial distribution, which takes in 2 parameters, r and p. R stands for the number of successes we are waiting for, and P is, like before, the probability of success on any one given trial. We have already seen 3 distributions, the binomial, the geometric, and the negative binomial, arising naturally from a Bernoulli process. Now let's see a 4th one, the Poisson distribution, and let's see how it arises as an approximation to the binomial when its 2 parameters n and p happen to be such that n is relatively large and p is relatively small. So we are looking at a Bernoulli process like before, where in this case we're taking the probability of success to be 0.06, so a much smaller value than before. And each experiment now consists of counting the number of successes in 50 trials. So in the first experiment, in the 50 trials we explored, we saw 3 successes. So we'll record 3 as the realized value of the binomial random variable of interest in this case, with n equal to 50 and p equal to 0.06. And then we'll repeat this experiment again and again, like before, until the empirical distribution materializes. A comparison of the relative frequencies with the theoretical probabilities shows a close alignment between the two. And let's unpack for a moment one of these theoretical probabilities, one of these blue values, and notice that in the computation of that probability, there is a very large number, which is the combinatorial term, in this case 50 choose 4, and a very small number obtained as the product of fractions raised to high powers. And when we multiply all of these together, we get that reasonable value of 0.17329. If we didn't use the exact binomial probabilities, but instead approximated them using the Poisson distribution, we would get the probabilities in green. And you can see that in this case, those probabilities are quite far from where they should be, the truth told by the binomial distribution in this case. And that is because this Poisson approximation works best when the 2 parameters of the binomial distribution are such that n is very large and p is very small. So let's nudge our model in that direction and see how the Poisson approximation fares in that case. So what I've done here was to multiply n by a factor of 100 and divide p by a factor of 100, effectively keeping the product n times p constant at 3, but making n larger and p smaller, as that Poisson approximation of the binomial requires for it to work well. And notice that this time around, the Poisson approximation is incredibly good. And what makes the Poisson approximation to the binomial even more impressive is that it makes the computations a lot easier. Let's see this in action. Let me just start by turning everything blue here in the bottom so that we can relate this blue value here that we computed to that coming out of the binomial probability. And notice that it involved this combinatorial term here, which is a huge number, and then these fractions, which would have been a pain to compute in 1711 when De Moivre first stumbled upon the Poisson approximation to the binomial. Okay, and let's take a look at the computation of the probability coming out of the Poisson approximation. So how do we get that value? Well, first let's write out the PMF of the Poisson approximation, where in the approximation, notice that this lambda is taken to be the product of the two binomial parameters n, p. So n times p is 3. And so let's continue writing the PMF of the Poisson down here. So we have the constant e to the power of minus lambda times the ratio of lambda to the power of lowercase x over x factorial. So what this says is that if we have a random variable capital X that has the Poisson distribution with one parameter lambda, then the probability that this random variable capital X takes on a particular value lowercase x is given by the PMF expression on the right. And now let's evaluate it for the particular value of interest. In this case, we're interested in the case when lowercase x is equal to 4 and our parameter lambda is equal to 3. Then we get e to the power of minus 3 times lambda, which is 3 to the power of 4 over x factorial, which would be 4 factorial. And when we evaluate this expression, we get 0.16803136. That expression that we have here as part of the Poisson approximation. Notice that this calculation here at the bottom involves very small numbers, 3, 4, whereas the binomial one involved this huge combinatorial term, 5000 choose 4, and these tiny fractions raised to high powers. So the process of computing the binomial value in this case is much more complicated than the process of computing the Poisson approximation, and notice how good the Poisson approximation is. So if you were facing this problem in the real world, unless you need some incredible precision, going with the Poisson approximation rather than computing the actual binomial probabilities is probably the way to go here. I already mentioned that the Poisson approximation to the binomial was first recognized by De Moivre in 1711, but it took another 119 years until Simeon Denis Poisson in 1830 formally introduced the Poisson distribution as a legitimate PMF in its own right and not just an approximation to the binomial. And there's a process known as the Poisson process, which gives rise to an entire ecosystem of probability distributions around it. Imagine that the trials of the Bernoulli process that we are looking at right now represent us playing a lottery, and we play the same lottery every day, and the Bernoulli trial gets a value of 1 if we win the lottery and a value of 0 if we lose this little lottery. Now suppose that on a Saturday and a Sunday we were away for the weekend and we did not play the lottery. So trial number 12 took place the Friday before that weekend when we were away, and the fact that trial number 13 will be the one that will take place on Monday is perfectly fine with the Bernoulli process. The trials in a Bernoulli process do not need to be equally spaced in time, so that is perfectly okay. All that the Bernoulli process captures is that these trials took place and these trials are numbered consecutively. But clock time or calendar time does not play a direct role in the Bernoulli process. Okay, I'm excited to finally be able to turn now to the Poisson process, easily one of the most important processes in all of probability and statistics, which will give rise to an entire ecosystem of distributions around it, such as the Poisson distribution, the exponential distribution, the gamma distribution, which are easily some of the most important distributions to understanding the real world phenomena around us. And these are distributions that are so influential in the whole ecosystem of distributions that they have a tentacle in just about anything. So let's take a look at what a Poisson process is. I mentioned that a lot of real world phenomena follow the Poisson process. So why is that? Well, we're going to state 5 conditions known as the Poisson postulates. Any process that satisfies these 5 conditions will have random variables that have a Poisson distribution, as I'll explain in a minute. So let's get started with these postulates one at a time. The first postulate is trivial in terms of its practical significance, but is a technical necessity, so we need to state it. So we have our time axis down here, and this is time 0 when the process begins. So all that this postulate says is there must not be an arrival at exactly time 0. Of course, we have a continuous time axis here, and the probability of there being an arrival at exactly time 0 would be negligible, and we're just stating that formally because we need it as a technical requirement. So state it. Now let's move on to the more important ones. The second postulate says that the random variables that are measuring the number of arrivals over disjoint time intervals are independent. Okay, that's a very important one. So let's take a look at what that says. So we've got our time axis down here. So let's pick a time interval of length L1 here. And let's pick another, now we need disjoint time intervals, right? This second postulate works over disjoint intervals. So an interval L2, let's say there's another interval L3 here, and that should be enough. So we have disjoint time intervals. Therefore, what this postulate requires of a process for it to be a Poisson process is that the random variables that are counting the number of arrivals over these time intervals be independent. So x with an index of L1, x with an index of L2, and x with an index of L3, these are different random variables. They're capturing the number of arrivals over the respective time intervals of length L1, L2, and L3. Because these time intervals L1, L2, and L3 are disjoint, these 3 random variables that correspond to these intervals must be independent. That's what this second postulate requires of a Poisson process. Now let's take a look at postulate number 3. Postulate number 3 says that random variables that are measuring the number of arrivals over time intervals of the same length are identically distributed. So Let's see what that says. On our time axis down here, I'll pick an interval of length L1, and maybe over here I'm going to start another interval, and now it has to be the same length as L1, so that looks about right. So this one is of length L2, and then we could have another one here, an L3, and I've drawn these, that's important, so that these intervals are of the same length. L1 equals L2 equals L3. Because this postulate says that if we have time intervals of the same length, then the random variables that are measuring the number of arrivals over these intervals, right? So there's a random variable measuring the number of arrivals over the first interval. We can call it Lx with an index of L1. There's a random variable that measures the number of arrivals over interval L2. We can call that x with an index of L2. And this one here is a random variable called x with an index of L3. So this postulate says that these three random variables must be identically distributed. They must have the same distribution. We haven't stated what it must look like, just that they must have the same distribution. Notice that in this third postulate, there's no mention of disjoint time intervals, so I've drawn the interval L2 on purpose to overlap with the interval L1, just to underscore the fact that this postulate does not require disjoint time intervals. And notice now that postulates 2 and 3 taken together give us some IID flavor here that should remind us of the IID conditions in a Bernoulli process. Right, in a Bernoulli process, we required that the Bernoulli random variables be IID. And here we start seeing that there is an analogous IID flavor to a Poisson process. Okay, now let's turn to postulate number 4. And notice that I wrote this one in orange, and the fifth one will also be written in orange. And the reason for it is that the first ones are sort of the macro postulates because they require something on a bigger scale, and postulates 4 and 5 will be on a micro scale because they require something to be true over tiny little intervals. Okay, so postulate number 4 says that there must not be any simultaneous arrivals. So the way we can think of it is, imagine that we pick an interval of length t here somewhere. So this is an interval of length t. And now we'll pick this right endpoint of this interval and we'll start to gradually move it towards the left endpoint. This postulate number 4 could be written mathematically as the following statement. The limit as t approaches to 0, as the length of this interval t, of this time interval t approaches 0, of the probability that the random variable, which measures the number of arrivals over this interval, which will denote xt, the probability that this random variable xt is greater than 1, it's a ratio here where we're going to divide by t, is equal to 0. So again, so what does it say? It says that if we pick this right endpoint of this time interval and we start moving it progressively closer to the left, where this interval is shrinking to a tiny little interval, then essentially the probability that we'll see more than one arrival over this tiny little interval here is 0. It says that as t goes to 0, the probability that xt is greater than 1 goes to 0, and it does so even faster than the rate at which t goes to 0. And since we started making parallels to the Bernoulli process, This no simultaneous arrivals condition is very interesting because in the Bernoulli process we can only have a 0 or a 1. You can never have the outcome of Bernoulli process be a 2, right? So this fourth condition here says xt cannot be greater than 1. It can be 0 or 1. So that is looking pretty interesting. Now let's take a look at the fifth postulate, and then we will have seen all 5 of them. Okay, the fifth postulate says that the arrival probability is proportional to interval length when the interval is small, very small. In other words, if we pick a tiny interval, say this interval here is of length t, and then twice that interval would be of length 2t, and if we let the random variable x with index t be the random variable that is going to count the number of arrivals over this interval of length t, and we'll let x with an index 2t be the random variable which will count the number of arrivals over this interval of length 2t. What this condition says is that the probability of arrival over the interval of length 2t is approximately 2 times as large as the probability of arrival over the interval of length t. More crudely, the longer the time interval, the greater the probability of arrival, but this says a lot more than that. It says that as we increase the time interval, the probability of arrival increases proportionally, and that constant of proportionality is actually quite special. So let's write it out here. So mathematically, this statement says that the limit as t goes to 0 of the probability that xt equals 1 over t is equal to lambda. Remember that lambda is the one parameter of the Poisson distribution, and it gives us the average arrival rate. These are the 5 Poisson postulates, and any process that meets these 5 conditions is a Poisson process, and we will see that it will give rise to the Poisson distribution, the exponential distribution, and the gamma distribution. So let's take a look at that. Okay, so with the Poisson process, our perspective is always a passive one, so we're passively observing this process. At this time, we don't even know that it's a Poisson process. It's just a continuous random process, and we're noticing some arrivals. We're choosing the a minute to be the time interval of interest. So here, during the first minute, we counted 1, 2, 3, 4, 5 arrivals. So we'll note that as the realized value of the random variable of interest here, which is the number of arrivals per minute. Since I am simulating these arrivals, I should disclose that I am using an arrival rate of 3.6. In other words, 3.6 arrivals should be expected per minute on average in this random Poisson process. But we don't know that, and all we're observing is how many arrivals do we have during each minute, and that's what we're noting down. And then we'll just repeat this process, counting the number of arrivals during each minute. And why are we doing that? Well, think of it this way. This is a process we're observing, and we see that it satisfies the 5 Poisson postulates. If you remember, postulate 2 said that the random variables measuring the number of arrivals over disjoint intervals are independent. And we've partitioned the timeline here into independent 1-minute segments. Therefore, the random variables measuring the number of arrivals over these segments should be independent. And remember, postulate 3 said that the random variables measuring the number of arrivals over intervals of the same length are identically distributed. Every 1-minute time interval, in our case, is obviously of the same length as any other 1-minute time interval. And we have knowledge, or we assume, that these random variables have the same distribution so that it meets that third Poisson postulate. But we didn't say anything about what distribution that is, And by repeating now this experiment 100,000 times and letting the empirical distribution materialize, we will see what the distribution of the number of arrivals during a 1-minute time interval looks like. Having repeated this experiment 100,000 times, we obtained a sample of 100,000 realized values corresponding to 100,000 IID random variables with some distribution. And now the relative frequency of each value that this random variable takes is in yellow. It's based on 100,000 experiments. So if we were to repeat this experiment into millions of times, the relative frequencies in yellow would approach the theoretical probabilities listed in blue. And those theoretical probabilities come from the Poisson distribution with parameter lambda, where lambda is the average arrival rate per minute in this case. Let's remind ourselves of the Poisson PMF. The probability that x takes on the value lowercase x, given the parameter lambda of this distribution, is given by e to the power minus lambda times the ratio of lambda to the power of x over x factorial. So then, for any one particular value, if we evaluated for lowercase x equal to 3 and given a lambda of 3.6, which is what we used in our Poisson process, we get e to the power minus 3.6 times 3.6 to the power 3 over 3 factorial. And if we were to evaluate that, we would get 0.212469, which I'll just round to a 5 as the fourth digit after the decimal. And you can now relate this number to the one we have up here. Now, what if in a Poisson process, instead of counting the number of arrivals during a set time interval, what if instead we were interested in the time until the first arrival? What distribution would this random variable have? Well, if we repeat the same procedure as before, where we repeat this experiment of measuring the time until first arrival again and again up to 100,000 times and let the empirical distribution materialize, we'll see what it looks like. The distribution of this random variable, which models the time until the first success, is a very famous distribution known as the exponential distribution, and it has one parameter, lambda. That's the same lambda that's in the Poisson distribution. So both the Poisson distribution and the exponential have only one parameter, lambda. They arise from the same process, just asking two different questions about that process. And finally, what if we were interested not in the time until the first arrival, but in the time until the rth arrival? What distribution would this random variable have? We see that the empirical distribution approaches that of a distribution which is called Erlang, which is a special case of the gamma distribution. Now let's have a look at why the normal distribution arises so often in our work in probability and statistics and in the real world. We will study the central limit theorem in detail in chapter 5, and we're not prepared to discuss it properly now because it involves concepts such as the sample mean, which we have not introduced. We'll introduce that in chapter 4. But for now, all I want to say with this little animation here is that If we have many little random variables that are independent or weakly dependent, their sum will tend to be normally distributed. And if instead of adding these, we took the sample mean and we standardized it, then that standardized sample mean will follow the standard normal distribution. And this result holds whether the distributions that are added are continuous or discrete. It holds whether these random variables are identically distributed or not. It holds whether they are independent or weakly dependent. There are many flavors of the central limit theorem, and this same general result tends to hold. Okay, so far we've looked at only two processes, the Bernoulli process and the Poisson process, and we looked at one result, the central limit theorem. And yet, with only these three things, we've seen so many distributions come to life. We've seen the Bernoulli distribution. Of course, it's a central element of the Bernoulli process. We've seen the binomial NP distribution arise as the distribution of the number of successes in n IID trials, each with probability lowercase p of success. We've seen the geometric distribution as that of the number of trials until the first success. And we've seen the negative binomial distribution as the distribution of the number of trials until the rth success. So that's just the Bernoulli process right there. And then with the Poisson process, of course, we've seen the Poisson distribution, giving us the distribution of the number of arrivals during an interval of fixed length. And then let's switch to the menu of continuous distributions for a moment, because the waiting time until the first success in the Poisson process gave us the exponential distribution, and then the waiting for the rth success gave us the Erlang distribution, which here in the NumPy menu of distributions, it doesn't exist by itself, but we mentioned that Erlang is a special case of the gamma distribution, so I'll circle gamma as a distribution that we've seen arise from the Poisson process. And then we've seen the central limit theorem give us the normal and the standard normal, right? I could circle also the standard exponential because of course it's a special case of the exponential, which we've already circled. Standard gamma is a special case of the gamma, which we've already seen. And okay, so now that we've seen the normal arise from the central limit theorem, there are a number of distributions which are important only because they are related to the normal and because the normal is important. So distributions such as the chi-square, distributions such, and there's a non-central chi-square one as well. Distributions such as the student t are important only because they're related to the normal, which is important. F, non-central f, log normal, arguably. Log normal might have some importance that is also independent of the normal. You see that with just these three phenomena that we've covered, we can start seeing where some of these distributions on the menu come from. The Bernoulli process, the Poisson process, the central limit theorem are complicated results to be understood in full, but they are elementary in terms of what they apply to. Right? The Bernoulli process is just a sequence of Bernoulli random variables, each of which has only two outcomes, and there's a probability of success that's constant across these Bernoulli trials. It's a very elementary setup. Same thing with the Poisson, same thing with the central limit theorem. These are very elementary, and because they are so elementary, If there are scientists performing science somewhere on a planet in another solar system and they are as intelligent as the human beings on planet Earth, they almost certainly will have stumbled upon these same distributions. If they have some phenomena there that we don't have, they might have some extra distributions, but we'd expect our menu of distributions to be a subset of theirs. And yes, some of the distributions are an artifact of the lens through which we are looking at the world and not a reflection of the world itself, as we've already mentioned. We will see in the future chapters that the F distribution, the chi-square distribution, the student T distribution, these will arise due to our process of sampling, of collecting a sample and asking questions about it. So you can say that these distributions don't really model anything directly in the world. They arise because of the lens through which we look at the world. But it is so fundamental to collect a sample and ask questions about it that, again, if there are intelligent life forms on another planet in another solar system, they would almost certainly also think of sampling, and they will almost certainly once more stumble upon these same distributions. Before we wrap up, let's do one Monte Carlo simulation. Monte Carlo simulations are absolutely essential in the real world. In the classroom, a lot of the problems that we tend to solve are very cookie cutter. They've been designed so that they exactly work in a beautiful way. In the real world, a lot of times the math gets too involved, gets too much. Here's an example of a problem which seems simple, and yet if you try to solve this with a pen and paper, you'll find it extremely challenging. But with a simulation, we can solve it easily, and not only that, but the ability to see the empirical distribution with our own eyes, I think goes a long way, something that if we're solving this with a pen and paper, we wouldn't be able to draw. I borrowed this question from the wonderful textbook by Larson and Marx called Mathematical Statistics, and in particular from section 4.7, where this example is worked out in detail. What I really like about it is that in order for one to be able to perform this simulation correctly, one would have to know the story of the Poisson distribution, and one would have to know that the random variable which measures the waiting time until the first success or the first arrival has the exponential distribution. It is knowledge of these stories and how they're connected to the Poisson process that will allow us to perform this Monte Carlo simulation. And I think the result is quite beautiful and has practical significance, because you can take this problem from a warranty on a TV context to many other contexts that have real-life applications. And that's it for this video covering distributions. We've essentially covered the first 3 sections of Chapter 3. Section 3.1 was a very brief introduction, 3.2 was on discrete distributions, and 3.3 was on continuous distributions. Next is section 3.4 on exponential families, and I chose to defer this section until later because I think it's a little anticlimactic to cover it here. So if we postpone it and cover it after we cover sufficiency, then we will see that this result on exponential families is absolutely incredible, and we'll be able to appreciate it. So I'll defer that section until after we've covered sufficiency, so then in the next video I'll cover section 3.5, location and scale families of distributions. Thanks for watching, see you next time.